Yeah, I'm going to do some more probability, but I'm going to start with a concept that we're going to run into later, the basic counting law, because if you remember probability, we need to know the number of ways something can occur, and then we divide that by the total number of outcomes that we have in our sample space. So a large part of probability is just counting things. So we're going to learn to start counting. So here's a wardrobe problem. If you've seen me on these videos, that's about how many colors of stuff I have. So how many different outfits can we make? If we take our blue shorts, I can pair that with a green t-shirt, I could pair that with purple, I could pair it with red. So there are 3 outfits I can make. I can do the same thing with tan. If I have tan shorts, I can have my green shirt, I can have my purple shirt, I can have my red shirt. So the total number is I have 6 outfits. If I could count, if I could spell that. But I want to do the basic counting law. I want to show you this. Okay, here's one event. There's 2 ways that can occur. Here's another event, a second. And there's 3 ways for that to occur. I bet you see how we got the 6, because this gives me sort of the number of groups I have. I have 2 groups, and this is number in the group, which is 3. We did 2 groups times 3 in a group, we got 6. That's the counting principle with this demonstration. So it means, I'm going to paraphrase, if there are n ways for event A to occur, in this case, the shorts, and m ways for event B to occur, there are n times m ways for the total to occur. Now I'm doing this because I'm going to play with rolling 2 dice. So I'm going to roll 2 dice. So if you think of the first die, and you think of the second die, these are my events, there's 6 ways for this to occur. There's 6 ways for this to occur. So the total number in my sample space is 6 times 6 is 36. So I'm going to build that sample space, and then we're going to play with it to do some probability and some odds. So I'm rolling 2 dice. I want to build the sample space. I'm going to start with the first die like this. It can be a 1, 2, 3, 4, 5, or a 6. Then I'm going to add to that the second die. it could come up 1. So notice I'm getting all of these outcomes that have the second die 1 and then the first die being whatever it can be. You could do this the other way. You could flip it as well. So now the first die can also be a 1, 2, 3, 4, 5, or 6. And the second one can be 2s. Notice we now have 12 because it's 2 times 6. This is when I wish I had the cake in the oven that I could just take out and show you that it's baked. But no, we have to actually do this. I'll see if I can do this without making a mistake as I think ahead. Eat some popcorn. This is the exciting part. Okay, that's 30. I need one more column. Okay, I need a drink of water. Okay, 36 total outcomes. So what's the probability that we get a 7? That meaning add the total dots from my dice, they add the 7. Well, I know there's 36 total in my sample space. How many ways can we get a 7? Well, they happen to be up along this diagonal. And there's 6 ways. So that's the probability of when you roll 2 dice, you get a 7. It's 1 out of 6. What's the probability of getting a 2? It's out of 36. How many ways can we get a 2? Looks like there's only 1 way. And one more, how about the probability of getting an 8? See, 8s live on this diagonal, and there are 5 of them. So this is using the sample space to figure out probabilities, and these are classical probabilities. Now, should have cut and pasted that while I had it. What are the odds of, let's see, we're doing against. Odds against rolling a 7. Well, I know the probability of a 7 is 1 out of 6. So the complement, which would be probability of not 7, is 5 out of 6. We know odds against are probability of the complement divided by probability of the event is 5 over 1. We would write that as 5 to 1. Meaning you bet $1, you win $5. You should win if a 7 is rolled. Now I wish I had a picture of a craps table in Vegas, but here's what Vegas does. Vegas pays 4 to 1, meaning you only win $4. Again, Vegas makes their money. Everything is random. It has to be random. But they don't pay the 5. They pay the 4. They don't pay true odds. do not pay true odds. Okay, I'm just going to finish up, be kind of looking ahead to where we're going, foreshadowing, so to speak. What's the probability of rolling a 7 or a 4? Okay, I know there's 36 total outcomes. I know there was 6 ways to get a 7. I'm going to scroll back up quickly and do ways to get a 4. There's 3 of them. So the total number of ways I can get a 7 or 4 is 9, is 1/4. Notice what we did here. The word or, we ended up adding those probabilities. So this really is it was 6 out of 36 plus 3 out of 36, which was the probability of the 7, and I added the probability of a 4. So when we see or in probability, we start to think of add the probabilities. This is actually foreshadowing section 4.2, but as long as I'm here, let's go to a deck of cards. What's the probability? So let's stop for a second. Draw 1 card. Okay, that's our event. What's the probability that I draw an ace or a king? Well, we're learning that or means add. This is 4 out of 52 plus 4 out of 52 is 8 out of 52, and I'm just going to leave it out of 52 for now. So the next thing I'm going to show you, what's the probability of an ace or a heart? Well, if we follow this, probability of ace plus probability of a heart, there's 4 aces in the deck. There's 13 hearts in the deck. We get 17 over 52. Now I'm going to caution you, hopefully there's an alarm that went off. Because something happened here. Because we have an ace of hearts. It got counted here and it got counted there. It got counted twice. We have to subtract 1. So we really have 17 over 52, subtract the 1 that got double counted twice, we get 16 out of 52. I'm going to use a big word here in set theory. I'm going to use the intersection. Because what happened here with the aces, there's our set aces. Here's our set hearts. If we just count the 4 aces, we have one here, and one here. If we look at the ace of hearts, it lives in the intersection. It's where it overlaps. And then out here in hearts, we have 12 more hearts. The 13th is in the middle. So when we did probability of ace plus probability of hearts, that got counted twice. So we have to subtract out the intersection. That's the upside down kind of U, which I think I can make a little prettier. That means intersection. So that leads us into section 4.2.